This is another video in determining the numerical coefficient of a specific term, in this case a term with literal coefficient x to the power 4, y to the power 7, and z to the power 4 for the expansion of this trinomial expression. Even if it's a trinomial expression, we're going to use here the multinomial theorem to determine the numerical coefficient. Take note here that our n is equal to 15, that's the degree of our expansion. And we would be expecting the number of terms in this manner, n plus m minus 1 combination n. Again, we're not expanding it here, but I'm just going to add this concept so that we will be able to appreciate the multinomial theorem properly. For our m here is the number of terms, you have 3. Therefore, you will have here 15 plus 3 minus 1, taken 15. If we were just asked, okay, again, if we are just asked about the number of terms, so that's 18 minus 1, that's 17, combination 15. And if you're going to use your calculators there, you may use yours. 17 taken 15, we are expecting 136 terms. That's why if we are to expand this multinomial, or specifically trinomial expression, you would have a lot of terms. So generally, this problem will only focus on the numerical coefficient. So we're going to attack it on that manner. Just for the purpose of discussion, for the expansion of a multinomial, okay, raised to the power of n, this is equivalent to summation of the combination of n by n sub 1, n sub 2, and then n sub m, okay, and then you have your x sub 1, the first term, to the power of n sub 1, second term, as you can see here, first term, second term, n to the power of n sub 2, until your x sub m, so you have n to the power of m. This will be the expansion that will yield us 136 terms. But since we are just asked about the numerical coefficient, we are just going to use this portion in the formula. No need to identify the sum because we are to specifically find the numerical coefficient of the term with x to the power 4, y to the power 7, and z to the power 4 literal coefficient. How do we determine that? In this item, we know already our n. Okay, that's part of n here. And even if m is not of use in the determining coefficient, but we know our m being here. So the next one here is to identify what will be the values of our n sub 1, n sub 2, and n sub 3. Because we can see here it has an item for the combination here. How do we identify that? Looking into this perspective here, this one, this portion here, this connects to our literal coefficient. Hence, if we're going to compare that, x to the power 4, y to the power of 7, and z to the power 4 with x sub 1, n to the power of n sub 1, x sub 2, n to the power of n sub 2, and since we only have 3 elements or 3 terms in our multinomial, we have x sub 3 to the power of n sub 3. We would know that our n sub 1 is actually equal to 4. Our x sub 2 is 7, and our x sub 3 is actually 4. We also know that this is really part of the expansion because when you add all of this, it will be equal to n, which is our 15, which is our n originally. So with this in mind, we have now identified the correct n sub 1, n sub 2, and n sub 3. Hence, simply look into this as this is the result for your numerical coefficient. That would mean you're going to invoke here n combination n sub 1, n sub 2, until n sub 3, n sub m, but since we only have 3 terms, you have n sub 3, which is equal to n times, sorry for that, that's times, sorry, our n rather. Our n is already identified as 15, and you have here 4, 7, 4. Before we start solving for this, there is an important concept that we also need to learn, because aside from this combination 15, combination 4, 7, and 4, this is not the complete formula for the identification of numerical coefficient, because when you look at our trinomial expression, not all of them are having numerical coefficient of 1. Yes, x has a numerical coefficient of 1. Z has a numerical coefficient of 1. But for y, the numerical coefficient is actually negative 1. What's the purpose for that? The purpose of that is looking into this formula here where our terms are raised into exponents similar to this, or these are the exponents. But it's not just the variable or the literal coefficient. It would be the entire expression. I'm talking about subjecting the numerical coefficients to the same exponents because we have different values later on if we will not do so. I'm talking about here subjecting your x sub 1. Your x sub 1 is actually x. Sorry for that. X raised to the power of 4. Your y is negative y raised to the power of 7. And your z is actually raised to 4. Because when you do this one, this will be will use what do you call this one? Loss of exponents, specifically the power law, which will give us negative 1 raised to 7 and y to the power of 7. And this will bring us different result when multiplied to this item. This is also true if the numerical coefficients of our x and z are no longer equal to 1. Let's say this is 2 and this is 3. That would mean we'll also be subjecting this to the entire exponent to yield us 2 to the power of 4 and 3 to the power of 4. That would mean the numerical coefficient is not just this alone, but it's also a product of the numerical coefficients subjected to the process. Now, we will have an example for that as we move further, but generally here, the only change from the previous video is the presence of negative 1 for our variable or term minus y. So with that, let's continue. If we are going to continue here, this will become 15 factorial over 4 factorial, 7 factorial, 4 factorial. Of course, it has 1, right? So 1 to the power of 4, or just simply 1. Negative 1 raised to the power of 7. You also have 1 here, 1 to the power of 4. And you will have x to the power of 4, y to the power of 7. No longer negative because your negative is already here. And z to the power of 4. This is the intended literal coefficient discussed here. So basically, we are going to the right direction. This may no longer part of the process, but this is an indication that we're doing it right. Okay? This is also the reason for that. So we will be continuing that, of course, that we become negative. Negative raised to the power of odd exponents negative. This is positive, positive, so negative. 15 factorial over 4 factorial, 7 factorial, 4 factorial. Because if you are not going to include that, you might give an answer which is positive, and definitely it's incorrect. You can verify that if you would like to using the expansion, but you will be expecting 136 terms. So just bear in mind those important coefficients. As mentioned in the next videos, we will be having more values for numerical coefficients for terms, not just 1 and negative 1, for us to really look into the process. Now, for this, simply try to finalize that. You can do it at once in your calculator, but I'm going to do it step by step for our I'm just going to do it at once because 15 factorial is very large. I can no longer write that, but let me use other form of calculator here. 15 factorial is equal to 1, 2, 3, 4. 1,307,674,368,000 over your 4 factorial is 24. You can verify that. Okay, it's 4 factorial is 24 times 7 factorial is equal to 5,040 and another 24 here. So you can verify the result. Your denominator, let's start with denominator first. 24 times 24 times 5,040 will get a result of 2,903,040. Again, this is negative and our numerator is still 1,307,674,368,000. So if we're going to divide that, 1,307,000, take note it's negative, 1,674,368,000 divided by 2,903,040. You will get a result of negative 450,450. So the difference for this, if you're not going to consider the negative sign as part of the process here, so that will be positive, obviously there it's very incorrect. This is the literal coefficient, this is the numerical coefficient of the literal coefficient x to the power 4, y to the power 7, and z to the power 4. We don't need this again because we're looking for numerical coefficient, but I'm writing it here as a basis of the flow of our process. So the difference of this from the previous video is the existence of negative sign, and the difference of the next few videos is where we are going to integrate other numerical coefficients for our trinomial or even multinomial if we have soon. So this is how different is this from the previous video, as even if we are going to have the same process, we are using this as in general because our numerical coefficients for the terms are no longer equal to +1. Thank you very much for watching.